Good evening, sir. My name is Mutsaka Emmason, and our part which was assigned to us was quantum reinforcement learning. And I'm going to go a bit of it, introductory part of it. And my colleague, whom we worked with, will continue from where we stop. So I'm going to talk about how quantum computing enhances reinforcement learning, that is making it more efficient for complex problems. Then briefly, let me outline the structure, how it is going to be like. Definition, we're going to talk about the definition of quantum reinforcement learning, of reinforcement learning basics, and then applications. And then from there, you go to some few goals that I managed to get for the implementations. So I'll begin with the definition, whereby this one's just basic, whereby quantum reinforcement learning, it is a hybrid approach that integrates quantum computing with reinforcement learning to enhance computation efficiency. So that's what this definition is talking about. So like it references quantum mechanics to improve learning efficiency, and then a computation speed, and then the scalability. So like I will go to, after the definition, I will go to the motivation part of it, whereby we have the classical reinforcement learning algorithms to go with the high dimension set action spaces and a slow convergence. Then the quantum computing, it offers parallelism and superposition to accelerate reinforcement learning. Then from there, I'll talk about the new optimization techniques, like the quantum variation algorithms that enhances efficiency. For this one, for it uses, like, it works like how the neural networks works. That's how they represent the real world models. Then you have the applications include why this quantum reinforcement learning is applied. You have finance, we have, that is banking sector, we have robotics, whereby you can develop your model to detect like a disease in agriculture. We have an AI-driven automations. We have like the vehicles which are automatic. Then I go to the goals of this quantum reinforcement learning, whereby it improves the reinforcement learning efficiency using the quantum computing, as I have talked about, I talked in the previous slide, that the quantum computing, for it improves efficiency. So I'll talk about our goal is to reduce computational complexity. This quantum parallelism allows faster decision making. Then it increases generalization capabilities of reinforced learning agents, whereby it can generalize better in multi-state environments, whereby you have the environment which is hotter, we have cold environments, but for it co-works there. Then our other goal is to explore the potential of quantum advantage in AI. Then I went to the background and then the context, whereby the overview of the reinforcement learning. For it's where an agent interacts with an environment to maximize the cumulative reward. So by the components of the state S representing the environment, I have the action, you have the reward, feedback, you have the policy strategy for action selection, you have value function measures expected cumulative reward. Then from there, I will talk about another thing, which is the overview that I'm still continuing with the above thing, that the quantum computing is a principles like the superposition, entanglement, and then the quantum parallelism to enhance efficiency. Then I talk about the quantum circuits, which is called the RL problems efficiently. Then the quantum algorithm exhibit computation speedups in optimization and research problems, such that when you develop those models, like let me say you are developing a model to detect a disease in your tomato plantation. So for these quantum algorithms, for them, they optimize that such problem such that it can be easily implemented. Then the history, we have the high quantum computing concept began in 1980s. Then 1940s, we had the algorithm which was demonstrated quantum speed up. We have the 2010s, we have the variational quantum algorithm that you want to imagine that uses neural networks. 2020 is quantum real reinforcement frameworks combined with deep learning and then quantum neural networks. Then the recent work is the hybrid QL models tested in quantum simulators. So, like the quantum reinforcement learning, like for it is an ongoing area of research with recent advancements in hybrid. So I talked about the quantum bits and then the quantum registers, whereby the bits explain the differ for them the bits they differ from the classical bits because they exist in the superposition of the quantum bits exist in a superposition of states. Let's say, as we said above, the state for it is represent the state represents the environment whereby you're going to apply your models. Then I also talked about the quantum registers, whereby the collection of the quantum bits which enable entanglement and then the parallel computation. So for it is to gather and then perform competition is efficiently. Then you can see the diagram. There's a sphere representation of the quantum bits and then the quantum registers. Then you also want to get quantum gates and then the circuits. Quantum circuits, for them, they are a collection of quantum gates used to manipulate quantum bits. Then we have the hard-mad gate. H creates the superposition. The Pauli gate, which is defined by three variables x, y, z bit, and then the base flips. The CNOT gate entangles quantum bits. Then the quantum Fourier transformation, the QFT, for faster computation. Then it is represented in this circuit. As you can have a look at this circuit. Then from there, I went to the Markov decision processes, where the MDPS, whereby it allows machines and software agents to determine ideal behaviors. Like how your model is going to behave, like with the people, like you are developing your robot. How are you going to make it? How are you going to combine all those things, like to work, to go work, like to behave like as if it is a human being, those being behaviors. So we have the states, we have the world state, a set of possible world states where the model is going to work from. That's the environment. The action is a set of possible actions, reward function, a reward function. That's the S and A. Then the policy and solution to that problem that you are trying to solve. So I came up with the sample model, like a picture here, which summarizes what is in the text here. So I can go to reinforcement learning, whereby in reinforcement learning, the agent interacts with the environment to maximize cumulative rewards over time. Then you have the actions and then the states. That's the agent's actions influence the state of the environment. It depends on the model you are coming up with. It's going to how is it going to like influence the state of the environment that's going to work in from. We have the rewards. That's based on the states. The agent receives rewards or penalties. Then we have the last point, the learning process. The agent learns optimal behavior through trial and error interactions with the environment. Then this is the visual representation of the reinforcement learning algorithms. This one, that's the flow chart. Then I can go to the exploration or exploitation trade-off, key strategies for it. Like it is insertion. This thing, it is insertion in reinforcement learning. Reason being, it has three strategies, key strategies. We have the correlate probability for random action, high probability for best action. Then we have another one, which is the upper confidence bound, balances exploration, and then the exploitation. Then we have the Thompson sampling, uses probability distributions. Like you get different samples from different states, then you sample them. Then this is a code. I will explain, like I will show my much in the code. This is the output for it, but we shall see it practically. Then you have the hybrid quantum classical RL reinforcement learning. For it, it is a classical framework for quantum enhanced components of the variational quantum circuits which replace the neural networks. So we can go to the next slide, which is talking about the hybrid quantum classical real learning, reinforcement learning, which combines quantum computing and classical computing to solve reinforcement learning problems. Then it uses some key components, which is the quantum processor handles complex high-dimension set problems, which then performs quantum operation, for instance, superposition and entanglement. Then we go to the second one, classical processor, manages control flow and decision making. Can move to the process to first initialize your problem. After that, you define where are you going to put your model. You define the environment, and then after defining identifying the environment, you take there your model or the agent that you have developed to solve the problem that you are having. Then after there, you simulate. Like you simulate simulations on to hit the possible actions and then the outcomes. Then the last bit of it, it explores multiple states simultaneously due to quantum parallelisms. Since you have combined the two, then you have the variation quantum circuits. This one, they are like parameterized with the quantum gates here, but we shall also see the output in the code with time. Then the quantum deep Q network, and for it replaces the deep neural networks in the deep learning, Q learning. It uses quantum policy optimization techniques to be in position to solve problems. Then you went to the applications, whereby it is applied in finance modeling, that is the portfolio optimization, sorry. Then robotics, adaptive decision making, whereby you make your model to decide like it depends on how you program it, put it in your tomatoes to identify the raw and then depend tomatoes. Depend on how you model your agent. We have healthcare, drug discovery using quantum enhanced RL, reinforcement learning, then traffic optimization, efficient route planning. Like this route this time, or are we going to have congestion at this time? That's the planning. Then you have the future search directions, we have the hardware advancements, overcoming noise, and then the coherence. Then beta quantum reinforcement algorithms, that's the hybrid approach, which is the recent one. Then you talked about the scalability, how can it be in position to adapt to those quantum like reinforcement learning algorithms to complex environments. Then we went to the conclusion. That's the conclusion part of it. Then before I welcome my colleague to continue, like let me first of all like bring the code, like to see some implementations. Okay, some implementation is whereby you began with the classical quantum learning algorithm whereby began with the importing the NumPy as NP, which will handle the mathematical part of it, that is in the form of the arrays. Then we initialize the table whereby we had two states, like 5 states, and then the two possible outcomes. Then with the hyperparameters whereby you have the alpha, the learning rate, then the gamma, the discount factor, then the epsilon, the exploration factor. Then we went to simulating episode, whereby we created a function for episode in a range, which is you have to be in a range of like a loop over 100 training episodes. You had to loop like 100, yeah, you had to loop like 100 training episodes. Then state we have random on the readings. State equals random, read, rad int 01, that state in a random state. Then from there went to the random select whereby we use the while loop, and we chosen that if we use the if loop within the while loop, that if random dot is 0 less than that, then we take the action, we explore. Then after that, we choose the action with the highest Q value. Then from there, I went down, and then we simulated the reward to get the output. That's the example. That's, yeah, to get like the output, which is the updated state. Then from there, we used out another if loop that like a function. If state is equal to 4, then stop the condition, then done equals true. Then print trained, like the model has passed the training. Let me try to run. Now we see what we get in the output. So we can see the table that representing learned values for optimal decision making. We have initialized the trained Q table. This one, we have the 0 initialization part of 0.3, then up to where the code ends. So I also went to I also implemented this part whereby we had the data plotting, importing the matplot, whereby the strategy is the grid, like we are representing the grid, whereby the Samsung and then like the USB. Then the exploration is we have 0.1 to 0.5. Then the exploitation have 0.9 to 0.7. Then for it goes downwards. Then we plotted the figure size is 10 inches to 6 inches. Then the bar width must be 0.35. Index range, the length is in the strategy. Then we plotted the bars, whereby we plotted the bars, then we added the titles, strategy, probability, exploration versus exploitation in efficiency strategies. So we plotted it, then we displayed the graph by calling it PLT.show. So when I try to, let me clear the terminal, when I try to output, we are waiting for the output. Waiting for the output. This is the output, whereby you're having the exploration in the blue and then the exploitation in green. That is probability on our vertical. Then we have on x-axis, we have the grid, we have the strategies or the three. So that was the second implementation. So like I can close this, I clear the output, I go to the next thing. It was I implement something here. This one is also obstructing for the hybrid quantum kaleidoscope, whereby I began with importing the panel which is used in quantum computing, and NumPy as I explained above. Then we define the quantum mode with panel length. Then the n cubes is 2. Then from there, the default is wires n cubes. Then from there, we define the quantum length theta, whereby you have to rotate on quantum orbit of 0. Then you also rotate on quantum orbit of 1. Then from there, we measure the octet point as 1. So this is the code, and let me try to run, and I will see also the outputs. And the output is here that we began from step 0. So every 10 steps, it prints the cost function to track the training progress. Then the final optimization p-value, it represents the learned quantum policy. As we have seen, the optimized q value, key 0.9999, and then other values. Then also implemented something in two networks, whereby because of limited time I will not go in every step of the code, but let me run it. As it runs, I explain a few things, like it combines quantum circuits with deep learning. Then it also the quantum layer here, it like uses trainable quantum parameters. Then you fully connected F layers, which handles classical processing, and then you optimized using P, Y touch, this one. The P, Y, we imported the touch, like the import touch, then it is initialized using it. Then from there we print trained quantum DQN model. So implying that when we see that on our screen, implies that the model has now it has printed it on our screen here, which I am highlighting in blue. That's trained quantum deep quantum networks model. So our model has has responded to our according to our expectation is. So that's the some of the few implementations, and I remain Emmason. Let me welcome my colleague to continue from where I have stopped. Thank you.
Good evening. My name is Apio Diane, and I'm going to be taking you through some concepts in quantum reinforcement learning. When we look at slide 1, we are going to look at superposition, entanglement, and parallelism. In certain environments, there are a vast number of states and actions, and traditional reinforcement learning methods kind of struggle to find optimal policies due to the size of the state spaces in these environments. And so this is where we employ quantum reinforcement learning that can navigate these spaces more efficiently on principles of quantum superposition, entanglement, and parallelism. And when you look at superposition, it's the principle that allows quantum bits to exist in multiple states as opposed to classical bits that exist in only 0 and 1, in only one state. And for entanglement, we look at the phenomenon that, for entanglement, we look at the phenomenon that occurs when qubits become interconnected in such a way that the state of one qubit or quantum bit can depend on the state of another, regardless of the distance between them. Then when you look at parallelism, we refer to the ability of quantum systems to explore multiple states and actions at the same time. And this is, you can say it's sort of basis of superposition. And when you go on to representation in quantum reinforcement learning, we can say that the environment is conceptualized using principles from quantum mechanics. And we in these environments we use quantum states and operations. For example, in this diagram, we have a representation of the Hilbert space, and A typically represents a specific concept of or vector, and S denotes the state, and the A union B signifies the union of the two concepts A and B, encompassing both the elements. And such frameworks allows for analyzing relationships and interactions among concepts within a geometric space. And when we look at such frameworks, the states are represented by S and actions by A, and they are represented as eigenstates, like within the Hilbert space, as you have seen. The action selection policy, which is like a strategy used by the agent to like choose the next state. We see that it leverages the collapse postulate, whereby actions in the superposition collapse, whereby actions in the superposition collapse into specific eigen actions upon measurement, with the likelihood of each action being determined by its associated probability amplitude. Probability amplitude, which will be touched on further as we move along. Then we look at quantum representation facilitates the use of TD, which is in full temporal difference, and it's a method for state value updating. And in this method, the value of the state is adjusted, value of the state, which is VS, V in brackets S, is adjusted based on immediate rewards and the estimated value of subsequent states, enabling the agent to learn and adapt its strategy effectively in the quantum environment. And when we move on to quantum Markov decision processes, it is a framework that incorporates quantum mechanics to model decision-making in environments where states and actions are represented using quantum states. We already talked about the Hilbert space, so I will not touch on it again. So I'll not touch on it here. Key aspects, certain key concepts to talk about here, like the Hilbert space, which I already touched on previously. But we can talk about the action space, which is represented by the letter A, defines the set of actions available to the agent, with each agent represented as a unitary operator that transforms the current quantum state according to quantum mechanics. About unitary operator, it is just a mathematical operation that transforms a quantum state into another quantum state, but preserving the magnitude of the state. Then we can talk about the transition probability function that specifies the dynamics of the QMDP. It reflects like the probabilistic nature of state transitions influenced by the different quantum state amplitudes. And we can talk about also the reward function that assigns numerical values to a state action pair and sort of gets like the immediate benefits of actions. And then you have the value function, which estimates the expected reward from a given state. And when we look at quantum reinforcement learning algorithms, we look at state collapse. We look at like the underlying ideas that are used to develop these algorithms. For example, state collapse, which I talked about in the previous slides. But we also talk about probability amplitude, which is a key component in quantum reinforcement learning, which involves updating the probability amplitude of the agent's policy using rewards received from the environment. In quantum reinforcement learning, probability amplitudes are updated using Grover iterations, which is a quantum search algorithm. And these Grover iterations update the probability amplitudes based on rewards received, allowing the agent to learn an optimal policy. Exploration exploitation trade-off in quantum reinforcement learning. So in short, I'm going to use EET. This is like the dilemma faced by an agent when deciding whether to explore new actions, which is the exploration bit, or leverage known actions that yield higher rewards, so like focus, which is like the exploitation. But this dilemma arises because exploration and exploitation are competing objectives. In quantum reinforcement learning, this dilemma becomes more pronounced due to the principles of superposition and entanglement, where these quantum agents can exist in multiple states at the same time. And so in turn, it also means that the agent's knowledge about the environment is, you could say, uncertain, making it harder to balance exploration and exploitation. A few approaches have been proposed to um, sort of tackle EET, and one of them, we talked about it, is probability amplitude. But there are other algorithms, for example, quantum epsilon greedy, quantum upper confidence, among others. Though this is a challenge, of course, there are certain advantages to EET, as seen in the slide. We can sort of also explain this graph. Basically, as we're still on this topic, so this graph kind of like shows how quantum reinforcement learning can use probability distributions to like explore a state space while still exploiting like the best strategy. We can see that the oscillation, so the oscillation diagram like shows the PDF of a quantum system, which is that red line, and then the PDF of a classic system, which is the blue line. So if we interpret this in the context, so if we're in the quantum system, so the quantum system, the nature of its oscillations represents like the superposition of the states, allowing like this quantum agent to explore multiple possibilities. And so we bring this back to quantum amplitudes to explore multiple states at once, leading to faster learning and more thorough search of the solution space. Whereas in like the classical system, that blue line, we can see a smooth kind of exploration or trajectory. And here we can see that an agent focuses on known optimal strategies instead of exploring new possibilities, as you can see for the quantum system, which is represented by that red line. For the implementation and simulation of quantum, I'm going to allow me to explain it at the end of the slide presentation. I'm going to be using Pennylane to simulate a quantum reinforcement learning system. But there are other tools as well that you can use. Talk about analysis of quantum reinforcement learning convergence. We first define it, and it's the study of how QRL algorithms behave as they approach an optimal solution. And like here, it involves examining conditions under which the QRL converges, the rate of its convergence, and the quality of that of the converged solution. And key aspects here, we look at optimal state value function. So algorithms converge to an optimal solution, which is the state value function that assigns the highest expected return to each state. And then when you look at optimality, we see that QRL algorithms can make optimal decisions with high confidence. And then lastly, when you look at physical realization, the algorithms can be implemented using existing quantum computing hardware and software. These characteristics demonstrate that QRL convergence is a well-behaved process that can lead to optimal decision making. Of course, quantum reinforcement learning is you could say inherently a new field, and future innovations are yet to appear and are yet to come up. So now I can show you the implementation. Like I said, I'm going to be using PennyLane, the library, the quantum computing library, and of course there are others, but for this simple simulation, I'm going to demonstrate using PennyLane. So this code basically is to train a quantum circuit to recognize patterns in binary data using basic learning algorithms. My colleague earlier talked about quantum circuits. So this quantum machine learning model attempts to learn the XOR function, which we are all familiar with. Using, so you'll see, adjust its weight, or you could say parameters, to minimize the errors between its predictions and expected output. So here we imported the libraries which we're going to use, and PennyLane is used to create and run quantum circuits, and NumPy is for numeric operations. So here we first, this line 5, create a simulated quantum device with 2 qubits. And when we look at this next sort of block of code from line 8 to line 15, so this is like a function that applies quantum operations. The first one, where we have the first line at line 10, so it rotates the qubit 0 based on the input 0. Second line rotates the qubit 1 based on the input 1. Third line applies an entanglement operation. Then this fourth line adjusts the qubit 0 using a trainable weight. And then we have this second last line, adjust the qubit 1 using another trainable weight. And here, the final return measures the qubit 1 to get the final prediction. And then you have input data, and then in this stored in this variable x, and then the variable y has expected output. So all this other code is training the model. That's from line 18. We are training the model. So when we look at this block of code from line 25 to line 46 that has nested loops in it, with this input XY pair, and then it runs the quantum circuit to get a prediction, and then it computes the loss, and then it updates the weight. It updates the weight using a basic gradient descent like rule. If the prediction is too high, the weights decrease. If the prediction is too low, the weights increase. So after training, this loops through the inputs X and prints the final predictions. So we can run this. This is the output during training, but we have our final predictions by the model, which we can clearly see resembles follows the principles of an XOR function, whereby after training they're supposed to resemble sort of like the output that an XOR function would output, or like close to the results that an XOR function would output. So we know that for an XOR function, it will output like the same number, which is 1 when inputs are different. So you can see here we have different inputs, and we have gotten the same prediction. And these results, of course, are not 100% accurate. Certain factors can affect different results. For example, maybe the design of the circuit can affect this prediction. Thank you.